Hello, statistics students. In our last video, we were introduced to the normal curve and how to find some values on the normal curve. We're going to continue that lesson today, so let's get started. Today's first problem, we are going to take from our textbook, page 246, the try it yourself problem at the bottom. And it says, the average speed of vehicles traveling on a stretch of highway is 67 miles an hour with a standard dev of 3.5 miles an hour. What is the let's see, a vehicle is selected at random. What is the probability that it is violating the speed limit of 70 miles an hour? Assume the speeds are normally distributed and are represented by the variable x. So remember our, our procedure that we learned in the last video. State the problem in terms of x, restate the problem in terms of the standard normal variable z, draw a graph shading in the appropriate area, and then use our table to find the area under the curve that we're looking for. So we were told that, let's see, mean 67, standard dev 3.5. And it's normally distributed. So I want to know the probability that somebody is going 70 miles an hour or more. Or I said more than 70. It wouldn't change the probability at all, if you recall. If you're not sure why that is, ask me in class. So we state the problem in terms of the variable x. The probability that our randomly chosen car is going faster than 70. I need to restate the problem in terms of z, so I have to convert 70 to a z-score. So standard normal variable z is a value minus a mean divided by a standard dev. So we can see that 70 is 0.86 standard devs above the mean. It's 3 miles an hour above the mean. A standard dev is 3.5 miles an hour. So we are 0.86 standard devs above the mean. Correctly round your z-score off to 2 decimal places because that's what our table needs, z-score going to 2 decimal places. So now I need a probability that z is greater than 0.86. So down here in black, I have my x numbers, and in orange, I have my z numbers. So 67 is our mean, standard normal, that would be 0. 70, let's see, 70.5 would be 1 standard dev, because that's my inflection point. So 70 is just a smidge below that, so there's 67, there's 70.5. 70 is gonna have to be right about there. And we've already shown that 70 is 0.86 standard devs and 70.5 would be 1 standard dev. And I want the probability that x is greater than 70 or z is greater than 0.86, so I'm shading to the right. And what is this area under the curve? Recall that our table gives us values to the left of this number, to the left of 0.86. If we want the area to the right, we know that this area out here plus this area over here equals 1. Density curves have an area under them of 1. So we just do 1 minus, it's a complement. And if you look up z equals 0.86 in your table, you'll find the area to the left of that is 0.08051. So the area to the right must be 0.1949, which means there's about a 19.5% chance that a randomly chosen car on that stretch of road would be going over 70 miles an hour. Next problem, try it yourself, number 2 on the bottom of page 247. What is the probability that the shopper in example 2 will be in the supermarket between 33 and 60 minutes? All right, so we have to go back up to example 2. A survey indicates that for each trip to a supermarket, a shopper spends an average of 45 minutes with a standard dev of 12 minutes in the store. The lengths of time spent in the store are normally distributed and are represented by the variable X. A shopper enters the store. Okay, then they give you some problems there. And we want the probability that somebody will be between 33 and 60 minutes in the supermarket. So I want the probability that X is between 33 and 60. So if X is between two numbers, then Z has to be between two numbers. So I have to convert both 33 and 60 to Z-scores. Formula for a Z-score is your value minus a mean divided by a standard dev. So there's my value, here's my mean, here's my standard dev. 33 is one standard dev below the mean. 60 is 1.25 standard devs above the mean. So I want to know the probability that Z is between -1 and positive 1.25. Again, 45 plus 12 is 57, so this is my one standard dev mark. So I need to go a little bit beyond that to get 60 or 1.25 standard devs. Now, whenever you have a Z-score between two numbers, you take the table value for this number minus the table value for this number. The reason we do that is the table value for 1.25 gives me this shaded area plus this unshaded area to the left. It gives me the value of under the entire curve from 1.25 to -infinity. So it gives me all this area. The table value for -1 gives me the area under the curve from -1 to the left. So this table value, 0.1587, which I get from looking up -1.00 on my table, that gives me this white area. The table value for 1.25 gives me the shaded and the white. The table value for -1 gives me the white. I subtract those and I'm left with just the shaded area in between. So the table value for a Z-score of 1.25 is this number. The table value for a Z-score of -1 is this number. And I get almost a 74% chance that somebody would be in the supermarket between 33 and 60 minutes. Something I want to make exceedingly clear. There's a difference between a Z-score and a table value. They are not the same thing. The Z-score tells you how many standard devs you are away from this mean. So the Z-score is just on the x-axis. How many standard devs are you away from the mean? The table value is the area under the curve to the left of that Z-score. So to the left of 1.25, which is the shaded area and the white area together, the area under that curve is 0.8944. The area under the curve to the left of -1, my Z-score is -1, the area under the curve to the left of that is 0.1587. Sometimes people will confuse those. A Z-score tells you how many standard devs you are from the mean, and the table value is an area under the curve. A Z-score can be greater than 1. A Z-score can be negative. Areas under the curve can never be because they're essentially probabilities. All right, come to class with questions. And